Hello everyone, my name is Sorn. Today I will present a paper named TPT or Test Time Prompt Tuning for Zero-Shot Generalization in Visual Language Models from NeurIPS 22. But before we dig deeper into TPT, there are a few topics that you should be familiar with. First is pre-trained visual language model. In this paper, we're going to mainly discuss about a model named CLIP. CLIP has two main components, text encoder and image encoder. It was pre-trained on a very large dataset of image-text pair. The goal is to predict which text caption matches with which image. Let me explain in more detail. In training process, each encoder will encode text and image to vectors. If text and image are matched, the model will be trained to minimize the difference between these two vectors. We keep training CLIP in this manner for a very large dataset. Once CLIP is trained, if image and text are matched, both encoders will have an ability to generate vectors that are similar to each other, and vice versa if they are not matched. With this ability, pre-trained CLIP can be applied to many downstream tags. One of them is zero-shot classification. Zero-shot simply means the model needs zero training data to perform classification. Let's consider the example of soccer and basketball image classification tags. Keep in mind that CLIP did not see these images in training process. What we can do is generate the text caption from class name. In this case, we add prompt, "This is an image of," in front of the word soccer and basketball. Now, we have both image text pair as before. So CLIP can encode text and image to vector using pre-trained encoders. Thanks to the knowledge from pre-training process, vector of basketball image should be more similar to vector of the word basketball. The same thing happens for soccer image. Therefore, we can make final prediction by choosing class that is more similar to the image vector. However, sometimes it's hard to tell whether image vector belongs to soccer or basketball. This means that the model has low confidence in this prediction. The question is, can we improve this zero-shot classification? Actually, this paper can. They generate more images by creating augmented views of each particular input. So the model has more information from different views of the same image by make a better prediction. Now, we can go further by trying to fine-tune the model in unsupervised manner. The objective is to make a final prediction more confident. In other words, minimize the entropy of the prediction. The remaining question is, which part of the model should we train? Is it text encoder, image encoder, or both of them? Or is it something outside the model like prompt itself? Surprisingly, modifying the component of the model degrades the accuracy. The only part that gives an improvement is prompt. We call this prompt tuning. Once we know where to update the model, we can further improve it by selecting only images vectors with high confidence prediction. Only those selected images vectors will be used to tune the prompt. Combining all these steps become TPT, the main proposed method of this paper. So in short, TPT has 5 steps. First, generate text caption from class name and perform image augmentation. Second, encode text and image to vectors using pre-trained CLIP. Third, select only high confidence prediction. Fourth, fine-tune prompt with selected vectors to maximize confidence of the prediction. And finally, predict the original image with the new prompt. We found that with these algorithms, the model gains some accuracy. This is the main result. The authors test the method on ImageNet and other datasets. The average accuracy gain is around 3 to 4% from the original CLIP as shown in the table. To conclude, TPT is the first prompt tuning method on zero-shot learning for visual language model. It can be generalized to other downstream tags, such as context-dependent visual reasoning. TPT gives relatively large improvement when the gap of distribution shift is large. However, there are some limitations of the paper. For instance, it sacrifices the inference time with model accuracy because of gradient calculation during test time. And also some of the standard dataset is missing in evaluation results, such as ImageNet C. Thank you for your attention, and I hope you guys enjoy my presentation.